Good morning, afternoon and evening for all listeners according to where you are. I would like to introduce our work, FlashRegex, to you. The authors are from University of Chinese Academy of Sciences, Institute of Software Chinese Academy of Sciences, Shenzhen University, the Hong Kong University of Science and Technology, University of Massachusetts Lowell and Shanxi Normal University. Next, I will introduce our work in 5 parts. First, background and motivation. Most of you are familiar with regular expression, or regex in short. It is widely used in various application scenarios in computer science for pattern matching such as programming languages, string processing and database queries. Though popularly used, regex are hard for users or even experts to understand and compose. Therefore, many works are proposed to automatically deduce regex according to given examples. However, we found that these existing works ignores the ReDoS vulnerability of synthesized regex, which may lead to safety-related issues.
By saying ReDoS vulnerable, let us first see what is ReDoS. ReDoS is a type of attack that will cause denial of service. By giving a carefully crafted string, an attacker can launch a ReDoS that exhausts the computational resources for the regular expression pattern evaluation. To provide a more intuitive idea, let's first see how a regular expression engine determines whether an input string matches the given pattern. For example, suppose we want to validate whether the given string apt matches the regular expression. The regular expression engine starts from the left point, searches the first group, take a path, suppose it is the lowercase a, then move on. It searches the second group, also finds a match, which is the lowercase b. Then, it reaches C, but it didn't match the pattern, so the regular expression engine will go back to group 2 again, evaluate the branches that are not reached before, then reach C again. It still doesn't match the string, so it goes back to the first group. Then, it first evaluates the branch that was not evaluated in group 1, then reaches group 2 again. Then it evaluates 2 branches in group 2 as well as C again. Finally, after we exhaust all possible paths but still fail to find a match, then we can conclude that the input string doesn't match the regular expression. Similarly, in example 2, the regular expression engine needs to exhaust all possible paths including 2 loops to conclude that the input string doesn't match this regex. Imagine the computational time will increase superlinearly with the increasing length of the input string.
A recent study shows that ReDoS vulnerable regexes are rather common in practice. They appear in the core Node.js, JavaScript, and Python libraries as well as in thousands of modules in the NPM and PyPy module registries.
Part of the result is shown in the figure. There are more than 10,000 modules are affected by ReDoS vulnerable regex, also known as superlinear regex, meaning which has superlinear worst-case complexity. Since it is often difficult for humans to reason about the complexity of regular expression matching, so we are motivated to develop a tool that tackles this problem when deriving regexes. Therefore, we propose FlashRegex, a programming by example (PBE) framework, which can automatically derive anti-ReDoS regexes by synthesis and repair from given examples. The key idea of FlashRegex is to reduce the ambiguity of regexes using deterministic regexes and the automata. Before we go into details, let me clarify some preliminaries. By saying Regex Synthesis, we mean that given a positive example set or a negative example set, the goal is to learn a correct and anti-ReDoS regex. Note that we say a regex is correct if and only if it accepts all the positive examples and reject all the negative examples. Similarly, regex repair is to repair an incorrect ReDoS vulnerable regex to be both correct and anti-ReDoS. A occurrence automaton is a specific type of finite state automaton which has at most states labeled with the same symbol.
As we can see in this example, suppose it is A2OA, then for symbol A and B, they appear at most twice.
Then we come to the core part, overview and algorithms. In general, FlashRegex can be applied to two application scenarios, namely, Regex Synthesis and Repair. For synthesis, there are two steps. One is KOA synthesis, the other is Regex extraction. After synthesis, FlashRegex will output the generated regex. On the other hand, for Regex repair, it takes a regex under repair in a set of examples as input, then after repairing, outputs a refined regex. Let's go into more detail. The first step in Regex synthesis, which is KOA synthesis, takes the given examples as input, and generate KOA. For example, suppose we want to generate a 2-way, suppose the alphabet only contains two symbols, A and B. Given a positive example, A, FlashRegex will first generate Boolean constrained formulas according to the given example, then feed it into SAT solver to find feasible solution. In this example, there are 4 feasible solutions, which can be visualized by their corresponding KOA, as shown in right-hand side. We can see all of these automata can accept the positive example. In the previous step, we derive a feasible KOA with respect to the Boolean constrained formulas. If there are several feasible solutions, return arbitrary one. Then, FlashRegex will extract a marked regex from the marked KOA. Finally, the unmarked regex will be output. Similarly, Regex repair also follows the same key idea, which is to use deterministic regex to avoid ReDoS vulnerability. There are 2 main steps in Regex repair. First, it converts the regex under repair to a deterministic KOA, then search its neighbors. The neighbors are those automata which can be reached by flipping one Boolean value in the adjacent matrix of the converted automaton. We want to find a better neighbor which can accept the most positive examples and or reject the most negative examples. Then repeat the search step until it finds a deterministic OA that can accept all the positive examples and rejects all the negative ones, or the number of iterations exceeds a given number, which is set to be 200 in experiment. Next, evaluation. We evaluate FlashRegex on benchmarks which are collected from 10 sources, as listed here. Note that different benchmarks have different features. For example, some alphabet size is much smaller than others, some only contains positive examples.
We released the source code and benchmarks on GitHub. They are now publicly available.
We compare with 5 state-of-the-art works. The first 3 are for Regex Synthesis, the other 2 are for Regex Repair. The experiments were designed to study 3 sets of research questions concerning FlashRegex's functionalities. Regex Synthesis, incorrect regex repairing, and ReDoS Regexes repairing in terms of efficiency, correctness and ReDoS vulnerability. Let me introduce them one by one. First, evaluation on Regex Synthesis. The columns represent the number of synthesized regex, the number of correct ones among them, the number of ReDoS vulnerable ones, and the average time taken by one regex. We can see that our work takes much less time, especially when the alphabet size is large. For correctness, we can see FlashRegex derives the most correct regexes, comparing with 6 and 14%. As for ReDoS vulnerability, 4 to 21 regex generated by the existing works are ReDoS prone. So summary to RQ1 is that FlashRegex can synthesize regex efficiently, correctly and safely. Second, the advantage of FlashRegex's efficiency becomes more obvious with the increase of the alphabet size. Besides, the results also confirm the lack of focus on ReDoS vulnerability in previous works, thus making further repair a necessity.
Then we evaluate the effectiveness of incorrect regex repair. We can see that FlashRegex takes about 1 second to repair one regex, with no ReDoS vulnerable regex generated. As a comparison, there still are more than 300 regexes are suffering from ReDoS after repair by existing works. Therefore, we can summarize that FlashRegex can repair incorrect regex efficiently, correctly, and safely. And the efficiency is not largely affected by introducing negative examples. Besides, after repaired by FlashRegex, the regex is free from ReDOS vulnerability. Finally, we evaluate the SL regex repair. Comparing with Refixer, FlashRegex took less time to repair, while Refixer took up to 3 hours to repair one regex. In addition, after repairing, 16 over 20 are still ReDOS vulnerable, while FlashRegex can repair all of them. We also compare with the repaired regex provided by experts. When examining 8 CV cases, we found that some fixes are not designed for regex, but for users' inputs. In addition, after repair, 2 of them are still ReDOS vulnerable.
Therefore, we can summarize that FlashRegex can repair ReDOS vulnerable regex efficiently and correctly. The experiment indicates the lack of attention to ReDOS in vulnerable regex repair. In comparing with the manual repair, FlashRegex works in an automatic and user-friendly manner, keeping users' intention meanwhile getting rid of the ReDOS vulnerability. Finally, we conclude our work FlashRegex as a PBE framework which integrates 3 functionalities. It is the first framework that integrates the synthesis and repair of regexes with the awareness of ReDOS vulnerabilities. Thanks for listening.